Good morning, everyone. So we were discussing about nitric acid, and today I will spend a few more minutes and wrap it up, and then we will go on to the next important acid, which is phosphoric acid, and basically talk about phosphorus and how important it is for agriculture, for fertilization. Last time discussed about the first part of the Ostwald process, which is taking ammonia and oxidizing it in presence of rhodium platinum catalyst to nitric oxide, NO. That's a very important step. The second step, which is the further oxidation of NO to NO2, is a non-catalytic process. It goes to NO2 and it's again an exothermic reaction. All of you have learned also in your school, presumably, that NO2 tends to form a dimer, N2O4, and that's also an exothermic process. Because it's an exothermic reaction, and also if you look at the stoichiometry, you can see that lower temperatures and higher pressure would facilitate the reaction, and that would be again true over here also, because 2 moles is going to 1 mole. So lower temperatures and higher pressures are beneficial from the conversion point of view. We did come across this particular reaction once before. Can anyone recall where we came across it?
So I'm not sure, but probably the lead chamber process.
Very good. In the chamber process, you remember that the rate determining step was really the oxidation of NO2. NO2. Oxygen was not reacting directly with the SO2. It was reacting with the nitric acid and NO2. In the process, it got reduced, and then it was oxidized by oxygen. That's what happened in the lead chamber process. Very nice. Once we have formed N2O4, then of course one has to introduce it to water, and then it converts into nitric acid. And as we discussed before, NO2 has a +4 oxidation state. Nitric acid has a +5 oxidation state, and therefore something else must be formed along with nitric acid in a reduced form, and that happens to be NO, the nitric oxide. So the same thing from which we are getting NO2, that again is reformed in part during the process of formation of nitric acid. So obviously there has to be some kind of a recycle loop so that NO again can be reconverted back into NO2. So that's important. And again, like in the sulfuric acid process, we have seen that all reactions were exothermic, including the hydration, the solvation of the gaseous oxide in water. Okay, and that also releases minus 103 kilojoule per mole, almost similar to the kind of reaction energies that you have in this step, going to NO2. So obviously there is a substantial amount of heat that is generated in the entire process of manufacture of nitric acid. And just like in the case of the contact process, that heat is actually utilized to generate either high pressure steam or power. And so again, just like the sulfuric acid plants, these tend to be cogeneration plants where you are generating power or steam additionally. So that's again something important to remember. Now, this reaction of NO going to NO2, which we'll be discussing a bit more, is a very interesting reaction. It's a third order reaction. We of course didn't discuss these when we were talking about the chamber process. It's a third order reaction. And interestingly, this is one of the rare cases where the rate actually increases with decreasing temperature. Normally from Arrhenius law, what we have learned, is that almost all, reactions, basically they proceed faster when you raise the temperature. That's generally true. This is one of the very rare exceptions where there is an inverted activation energy, and actually the rate increases when you decrease the temperature. So that way, it's a very happy situation because the lower temperature and higher pressure is beneficial for conversion, and the lower temperature actually doesn't hurt the rate of the reaction. So in every way, obviously this is a good situation, and that's why you would do it around say 40 to 50 degrees centigrade, which is basically 310 K. So that's how one would do the thing. But then because it's an exothermic reaction, this one, obviously there will be a temperature rise. So naturally, the extraction of to cool it down is very important for the conversion. Okay, so let us go through this process step by step, um, because we had found when we were talking about ammonia that ammonia you can isolate as liquid ammonia, right? I mean, last time we discussed that, and that's the easiest way to recycle all the rest of the gases. And because the ammonia is pressurized in the Haber-Bosch process, you really don't have to really lower the temperature extensively. It's a reasonable temperature range where it liquefies at 200 bar pressure, and so if you are integrated with let's say nitric acid production, obviously I will take the that liquefied nitric acid, and that is where I'll begin. You introduce ammonia as in the liquid ammonia form, because that's how you recover it from the Haber-Bosch process, and then you have to introduce air, and then you have an evaporator so that the ammonia is evaporated in a controlled way, so that you reach the required pressure, and the pressure that we are talking about is around 4 to 5 bar, that kind of a pressure. The air of course has to be compressed, and so you put a compressor and compress the air, and then you see what happens is that the presence of any dust and dirt, etc., can be a serious problem, especially when you're talking about the rhodium platinum catalyzed process, from ammonia to NO, and therefore you have to make sure that your vapors are properly filtered and there's no impurity, because if it poisons the catalyst, then you've had it. These are really filters to enable these impurities to get removed, and then you are introducing it into your catalyst bed, which, as we discussed, is the platinum rhodium alloy, the rhodium being added to reduce the loss of platinum because of evaporation. The alloy is more stable, and it also gave a higher conversion, presumably because there were no losses of platinum, so that also may have helped in improving the conversion. Because it is coming in a high temperature, as we discussed, and the high temperature was required, really, one is because we want to have a very high speed of reaction. The rate of reaction has got to be very high. The second, we had introduced pressure just so that the residence time in the catalyst bed is minimal, and you can see it is typically from 0 0.1 to 1 millisecond. The pressure obviously helps in having a higher flow rate through the catalyst bed. So it's going through over here, and because there's a lot of heat being generated. Oh, there's one more. As I said, I mean, the high temperature was not only for the high rate of the reaction, but to have substantial differentiation with the undesired reactions. and we had discussed the undesired reactions and which can form nitrogen, for example, from ammonia. And so we don't want that to happen. And so presumably at this temperature, you get the highest differentiation in the rates of the two reactions, because it's all controlled by kinetics, in this case. And then you have to remove the heat because a lot of heat is being generated. It's required because once I've formed the NO, then as we discussed, I mean, you have to rapidly cool it down so that the NO in the non-catalytic step can get converted into NO2. And so these are all means of heat exchange. Again, it's further cooled by exchange with another gas stream. I'll discuss what this gas stream is. So this is being cooled. So from hot, it's going colder. Okay. Now, it's still not sufficient, and so you may need to cool it further. And then what you're doing is that you are introducing it into water, okay, over here. So this is where nitric acid is forming. But the nitric acid that you get at this point is a weak acid. It's just about 30 to 35%. We will see the way in which BASF, again, they are the pioneers in this technology, and we will see how they kept adapting knowledge that they generated from production of sulfuric acid, even in the production of nitric acid. What you then do is, because you see the NO2 is going and you're forming nitric acid here, and as we discussed, it will also form NO. So part of it will get converted to NO. Now you are taking this NO over here, you're cooling it down, the gas stream, and you are pressurizing it to a higher pressure, because a high pressure really helps the NO2 conversion, low temperature and high pressure. So this is one pressure, 4 to 5 bar initially, and then the NO which is being released from the production of nitric acid is again repressurized here to something like 10 to 15 bar, and it's again introduced into a second absorber. Remember the way we really had those two absorbers in the sulfuric acid process, the double absorption, double contact process. It's being introduced here. There is some water which is being also put here. Really, partly, of course, the water is being used so that that reacts with the N2O4 which is being formed and forms nitric acid. But the water amount is controlled because in this absorber, you end up actually increasing the concentration of the nitric acid to something like 60-65%. So one is that it is the NO2 is really increasing the concentration of this weak acid, and also some more water is added just so that you are having a proper balance. When this stuff is again coming out, over here, this now is going to come out with about 65% kind of a concentration of nitric acid. And again, the same thing will happen. Again, NO will be formed, right? When HNO3 is being formed. Now, this NO, which is being formed, is again being put back for compression. So twice NO is being obtained, once over here, again over here. And what you do is that you purge it with air so that it strips off any dissolved gases which might be present in the final nitric acid. You take it out, like NO, etc. Some more air is being fed along with the NO that is being released. The air also is beneficial because you see, in the process of oxidation in all these points, naturally the oxygen in the air is getting depleted. So unless I have a sufficient concentration of oxygen, it will be difficult to convert all of the NO into NO2 in the second stage. So the air actually helps in that process, where you are effectively allowing the oxidation to take place, because if you have injected more oxygen in. So that's what you're doing over here. The nitric acid formation over here will be obviously favored when I'm cooling it. So these are all cooling systems which are reducing the temperature over here. But whatever you do, doesn't matter how hard you try, they will always, and this, remember, it's a counter current flow. So this acid plus some water, both of them are being fed into this, and the gas of this N2O4 which is being formed here is traveling up. So that's where the reaction is taking place. So that's happening, but these reactions are never 100% complete. There will always be a small amount of NOx which will escape. It could be NO because NO has also low solubility in the aqueous system, and some unreacted NO will escape. Or it could even be some NO2 which may have formed but which did not react or did not get dissolved in the water because of poor contact, and so that also could escape. So these are known as tail gases. So that's what is coming out over here. Obviously over here, all of this was cooled. Okay, so the gas which is going to come out here is going to be at a fairly low temperature, but there is a reason why we want to again heat it up, and I'll discuss that. So the tail gases are coming out over here. So the gases are being now heated first by the stream from here, which you're trying to cool, the NO2 stream, this one, and then it is being further heated up in this by passing it through this bed, because this bed is really hot, and there's a reason why we are trying to raise the temperature of this, which I'll discuss soon. And so it's coming out. It's now very hot, and it's coming out. Now what you do is you don't vent it out necessarily directly. Okay? You may think that I'll just vent it out, but actually, if the NOx emission is high, you'll have to bring it to a safe concentration, which means that I need to convert it into some benign molecules which won't harm the atmosphere. So that's another thing that you may have to do in case you cannot vent it out directly. Over here, what is happening is that you can see that that after this second absorber, the nitric acid that you're getting is something like 60 to 62%. The azeotrope of nitric acid is at 69% nitric acid. Okay. So what happens is that if you want to make concentrated nitric acid, very concentrated, then you cannot do it. You can at most go to 68 to 69%. And after that, it will just distill out azeotropically. So you're not really going to gain, all right, over here. The way in which you will actually concentrate it is with sulfuric acid. So you take concentrated sulfuric acid. The sulfuric acid absorbs water from the nitric acid. And now when you distill out, you'll get a higher concentration of nitric acid. So that's really the way in which you make concentrated nitric acid. You cannot just do it by plain distillation. So it has to be concentration with concentrated sulfuric acid, and then followed by distilling it to get the concentrated nitric acid. So that's really what you are doing now. And that's the way in which you make nitric acid. You are adding concentrated sulfuric acid into the nitric acid, and then what you do is that the sulfuric acid has a high boiling point. So it holds on to water very strongly. So the water is actually taken up by the sulfuric acid, and now what I'm doing is I'm distilling from that. When I distill from that, okay, what will happen is it will actually come off more like a very concentrated nitric acid, which will distill out from that mixture of nitric acid and concentrated sulfuric acid. Is that clear?
Yes, sir. So one more thing. So,
Yeah.
what do tail gases include?
Yeah, so tail gases would be what? I mean, so I'm obviously putting in air. So air will have nitrogen and oxygen, and all of the oxygen is not going to react. So there will be mostly it will be nitrogen, oxygen, unreacted oxygen, and the NO which was formed when N2O4 reacted with water to form HNO3, and also some of the NO2, N2O4, okay, which may not have reacted with water. Even if you know that spontaneously, of course, it will dissolve in water, but if there is not sufficient contact between your liquid gas phase, then the gas will escape. So some amount of the NO2, N2O4 will also escape in your tail gas. So there will be what all? There will be some moisture, there will be nitrogen, unreacted oxygen, and the NOx. Okay.
Yes, sir. Got it. Thank you, sir.
So then what you do is that you take this NOx, which is coming out, uh, and you may not be able to directly vent it, as I told you, but there are processes which are known, which convert the NOx into nitrogen, N2. So we, for example, did see, and this is so smart, when people do this, recycling that NOx, the tail gas, may not be a sensible thing, because you see, what will happen is that firstly, the concentration we are talking about are ppm concentrations. We are not talking about 10% of NO in that tail gas. We are talking about very small concentrations, and because there will be a large amount of nitrogen in that gas, and oxygen would be depleted, so I may not want to recycle that because I need more oxygen. So I'd much rather vent it out. What's the point in compressing nitrogen gas unnecessarily? So at some point, that's why recycle is not the wise thing to do, but getting rid of it, is the best option. So there are two ways this has been practiced. By the way, you would have heard of catalytic converters in the vehicles, because when these vehicles run, etc., they generate NOx and SOx and things like that. So those have to be really reduced, converted into safe chemicals, and that is what is done by these catalytic converters. Much the same is also applied to the process, and there are two reductants. The target is just like we saw, that how you convert a harmful chemical like ammonia into nitrogen, when we discuss breakthrough chlorination, when we are discussing water, wastewater. So in that same way, you can actually reduce NOx with hydrogen, okay, in a stepwise manner, and you can get nitrogen coming out, or which is probably better suited to the Ostwald process, because ammonia is my feedstock. I'm starting with ammonia, so you can actually react the NOx with ammonia in presence of oxygen, and it gets converted into nitrogen and water. Now, this reaction requires, one is that it requires catalyst, and the typical catalysts are the same catalyst, the platinum rhodium type of catalyst, okay, on silico-aluminate, except that the reaction conditions are different. You'll remember, that we talked about that if NO is in contact with the catalyst, and is also feed stream, then it's possible that it can get converted into nitrogen. There it was unfavorable. Here it is favorable. That's exactly what you want to do over here with the tail gas. So it gets converted into nitrogen. It's like a reproportionation because your nitrogen here is in a -3 state and here it's in a +2 state. So you are again reproportionating here and forming nitrogen, N2. This type of reaction with ammonia is known as selective catalytic reduction. And the one with hydrogen is known as non-selective catalytic reduction. Presumably because hydrogen can also react with other things and form other kinds of compounds. So probably the terminology of selective and non-selective presumably comes from that. But the sum and substance is that's what is done. It's converted into nitrogen before venting out, and because it's at a high temperature, this reaction, and that's why the tail gases need to be heated up. So you take advantage of the process heat and heat up the tail gases. Remember also these same concepts are applied over and over again. Like when I could not do much with my carbon monoxide and carbon dioxide when we were making the 3:1 hydrogen to nitrogen mixture by the steam reforming and air reforming process. At that point, what they decided to do was reduce those to methane because methane was found to be relatively harmless in the Haber process. And likewise here, I can't do anything, I can't recycle, etc. Okay, convert it into something benign, nothing better than converting it into nitrogen. Okay? So that's really the cleverness which all these processes are conducted. Now, the process that I described to you now is what is known as the dual high pressure process. There are nitric acid plants which are operating with atmospheric pressure process. The conversion, efficiency, etc. are not so bad. But the problem is that probably the rate of the reaction will be much lower in these cases. There's also an intermediate pressure process and the high pressure process. High pressure is I can initially itself pressurize my feed gases and take it all the way through, or you do it in two steps, like I showed you, that you do first at about 4 to 5 bar pressure and then later on at about 10 to 15 bar pressure. Now, the acid strength that you get in this particular process is higher, which is always an advantage. The conversion efficiencies are fairly comparable. Not really if you take all the way from ammonia to nitric acid, because that's the focus. Finally, you're trying to make nitric acid. You're not making NO2 or NO. But over here, you can see that you end up getting the highest overall conversion from ammonia to nitric acid. So these are the reasons why it's preferred. Also, the catalyst loss has been found to be less, the platinum loss in the dual process, which means that the very high pressures under which, let's say, you would do it in this particular case, actually it's found that it leads to a higher loss of platinum, whereas in this particular case, the platinum loss is less. Probably because the reaction temperature over here is lower. The Gauss temperature is 880 and here it's 930. So that actually may lower the thermal loss of platinum. Now, another is also they found that the Gauss life, the catalyst life, is quite good here. So if you look at this totality, this is probably the best way to carry out the process. Only thing is, it's a little more complex because there are two steps of pressurization. Of course, it doesn't say another thing which is so important, that the NOx emissions. The NOx emissions, if you have got high NOx emissions, then obviously that would not be a good thing. So that is the overall process. If you want to make 1 ton of nitric acid, let's say 100% nitric acid basis. So this is how much ammonia you require, 0.28 tons. You can work it out. Nitric acid has a molecular weight of 63, ammonia is 17, and you're taking 0.28. So 63 by 17 multiplied by 0.28, that comes to about 1.04 tons. So theoretically, you should get about 1.04 tons. You're getting about 1 ton, which means that you're talking about roughly about a 96% conversion, which is similar to what you found here. So the two data are consistent, and this is the how much air that you require, the normal meter cube of air in the overall process, because there are two steps of oxidation as we discussed, from ammonia to NO. That will of course take up a huge amount of oxygen, and then the second step takes up relatively less oxygen, the NO2, but overall the consumption would be very high. And you know, it's for this reason that I conceptually feel that this is not the best process in the long run. You know, in the long run, if you were making nitric acid, maybe to make it by something like the Birkelandite process, where you directly get nitric acid from air, you know, would obviously, at least in that sense, it would be more attractive if power related issues can be sorted out. So you'll also see that you get a steam credit, which is 1 ton at 10 bar pressure, and that's because of all the heat that is generated, which you are converting into steam, and you could either use the steam in some of your processes, or you can convert it into power and feed it to the grid. So again, a cogeneration plant, and this is the overall balance, you know, of mass and energy balance in this particular case. Okay. Now, so that brings us to the end of ammonia and nitric acid, and you can see, you know, that we have encountered in the process revolutionary things like the Haber-Bosch process, Ostwald process. Ostwald, who was one of the earliest Nobel laureates. I mean, every guy who has worked on it, they are the recipients of Nobel prizes for their work. You know? So it's a really very, very important process, and something I think that you should learn from and try to apply it, you know, in different places. You would have seen many commonalities among the processes, and try to, you know, make your mind laterally move from one application area to another, and see if you can apply it, you know. Now we will come to phosphoric acid and phosphorus. So we have covered the N. We are really covering it more from the fertilizer perspective. Nitric acid, of course, will give you ammonium nitrate, and ammonia, of course, will give you urea. I mean, these are the primary fertilizers. And likewise, all of NPK, the P, is really what about maybe about 80-85% is based on phosphoric acid. You know, fertilizers made from that. But in addition, as we know, you also require phosphorus not as a phosphoric acid, but you also require it for things like elemental phosphorus or matchstick and things like that, or if you want to make things like phosphorus pentoxide, P2O5, which is a very good dehydrating agent, drying agent. It's a you can make phosphoric acid from P2O5. It's got a whole lot of applications. It's used as a catalyst, acid catalyst, and also things like phosphorus trichloride, PCl3. And it's used to make a lot of phosphorus reagents. We will also discuss that all phosphoric acid is not necessarily produced by a single process. There are two processes for making phosphoric acid, and I'll discuss both. And when you are making a very pure phosphoric acid, and you need it like in food applications and things like that, you will actually derive it from phosphorus. Okay, so depending on the application areas, you get phosphoric acid in different ways. Now, let us look at where phosphoric acid and phosphorus-based chemicals go. You can see about 82% is actually going for manufacture of fertilizers. Very, very similar to to what we found with ammonia. Most of the ammonia is going for making urea or making ammonium nitrate. Okay, so similarly here, most of it is going for fertilizer. Some amount goes for animal feed because animals also require supplements of phosphorus. Industrial use is a big thing. I mean, like, although it's coming down now, but many of the builders, in detergents, they are what? They are orthophosphates. So these detergents, synthetic detergents, require builders to effectively reduce the hardness, of the water, because otherwise the detergents don't function well. Of course, there are ways of replacing orthophosphates with uh, builders like zeolites. You can use actually zeolite, and zeolites can pick up the hardness from water. So that would be one. So there's quite a bit of industrial use, as I told you, for PCl3 and P2O5 and things like that. And then a small amount goes as food additives. I think things like your Thumbs Up and Pepsi and Coke and all. They have phosphoric acid, and so in a way we are all drinking some amount of phosphoric acid. So that's the food additives area. It's used, and in the fertilizer area, there are different types of phosphorus-based fertilizers. The largest is diammonium phosphate, monoammonium phosphate. We will discuss about it. And then there's single superphosphate, which is another important fertilizer used, quite popular in India. And then, today people are making more complex fertilizers. So you might want to have a fertilizer with all nitrogen, phosphorus, potassium, sulfur all together. But then they are blended from things like this, so they are not unique fertilizers in that sense. Okay. So, but they are 21%. But altogether, if you add up these, you'll find that this total comes to about 82%, which is the bulk of all fertilizers that is sold. The feedstock for getting phosphoric acid is considered as a strategic material. Today, there is no other source but this stuff, phosphate rock. Phosphate rock is distributed all over the world, but some people are more fortunate to have plenty of it, and we have almost exhausted all our resources. We have virtually nothing today. It's a very vulnerable situation. And those are the places where countries need to make strategic decisions that whether you'll go and maybe buy some mines in some other countries in case they allow you to. And that kind of thinking needs to happen long in advance before people realize that they might see it as a good thing, selling off their some of their mines. So depends on at which point you make your strategic move. Okay. Now there are two types of this phosphate rock. It's called phosphate rock, or it's called rock phosphate. One is at the largest is this sedimentary deposits. In other words, this phosphorus and all this actually came from living organisms, okay, which had fossilized. So those are the sedimentary deposits which are found near river banks, ocean banks. So I mean, there are places where you get these deposits, and then there are some which actually come from volcanic eruptions. So they have got an igneous origin. These are typically fluoroapatite type of structures. That is, they will not only have the phosphate, but they will also have some other anionic counterions, okay, to the calcium. By and large, you can think of them as calcium phosphate. but they are not just calcium phosphate. Some amount of the phosphate is replaced with carbonate, with fluoride, with hydroxide, and those are the fundamental differences. I'll also show you how problematic this can be. You can view it as an opportunity or you can view it as a threat, and I'll show you what I'm talking about. Okay. Now, there are some rock phosphates, mostly in places like Norway, okay, uh, where what they have is they don't have the fluoroapatite, means this without fluorine. It's actually got chlorine in there. So that's interesting because fluorine seems to be doing a lot of damage to our environment. So if one could have substituted the fluoroapatite with chloroapatite, in some ways it would have been good, but these are present in very tiny quantities. I mean, the bulk of it is fluoroapatite. It's not this. Okay? Now, just to give you an idea that in 2018, 270 million tons of the rock phosphate, beneficiate rock, okay, was mined. So if you look at it, typically has about 30% of P2O5, as P2O5. So it gives you some idea that we are talking about around 80 million tons of P2O5 being used in agriculture. I mean, that's the kind of scale that these things are required at. Just to show you the distribution of this, the green ones are all the sedimentary deposits. So it's all sedimentary. But then in some places, you do find the igneous deposits, like for example, South Africa. South Africa has igneous deposits. We, for example, had phosphate rock. It's still being mined, mostly in Rajasthan. Okay? In fact, in places like Nagaur, they have got mines. But then I'll show you that it's not as if we had huge stock. Whatever we had, they more or less got consumed it all up. Okay? So we don't have much. Okay? Our neighbors are relatively more lucky that they've got more of the rock phosphate. But again, they are also in a bad situation. None of them are in a good situation. I'll show you the people who are actually quite blessed with rock phosphate, and in some of the African countries here. Okay, just so that you know what is the situation today. This is data from I think it was around 2018. Yeah, 2018. What was mine, and that's where I got my data of 270 million tons. Look at the situation. China, for example, had mined 140 million tons of rock phosphate, and we mined 1.6 million tons. And it's not that we mine 1.6 million tons because we just didn't want to do it. We just don't have the resources. It's going to last barely a few years. And even at that low rate of mining, okay, and you can see our current reserves, it will last us only 29 years if you only mine 1.6 million tons. And I'll show you our usage. If China continues to mine at this rate, what they're doing now, their stocks will also get depleted in 20-25 years. United States, I mean, they have actually reduced the extent to which they mine. Theirs also won't last that long. But if you take a country like Morocco, look at Morocco's reserves over here. Then you'll get an idea. They have got what? 50,000 million tons of rock phosphate, and they are mining at this rate, 33,000. They're conserving their resources, and so this will last about maybe about 1500 years. But they will be forced to increase the mining because all these countries will get depleted. Like the two biggest consumers of fertilizer are China and India. Okay? So if their resources are going to end, in 20, 25 years, where are they going to get their stuff from? They're already getting it from countries like Egypt and others, Togo, countries like that. So there'll be no choice but to have much, much higher levels of mining from Morocco. Whether they will permit it, I don't know. It could happen that there could be a war, at some point because of the need to control strategic resources. Just the same way, people try to do with oil. Okay, and the Middle East became so strategically important, for oil. So the Middle East is again in going to be, and Africa are going to play an important role as far as phosphorus is concerned. Now, this is again very important. This shows the rock phosphate from some of the major countries. BPL means basic phosphate of lime. Okay, that because effectively it is calcium phosphate. So that's known as phosphate of lime. Okay, so you can see the percentages of phosphate of lime in beneficiated rock. Okay, but these things also have one is of course the P2O5. Most of these NPK, when we say P, we typically will say how much of P2O5 the country is consuming. We usually don't say how much P is being consumed. Okay, it's expressed as P2O5. So if you look at the P2O5 in these rocks, we're talking about between 30 and 40%. In India, it's about 31%. That's about the amount of P2O5 that we have. Make a note of this. This is important. Okay, this is silica. You'll see it's not too high. There's a reason why I'm asking you to make a note of it. I'll show you later on. Now, fluoride is present in something like 3 to 4% by weight. It's quite high. And one has to ask, where is this fluoride really ending up? Now, not only that, if you look over here at trace elements, these phosphate rocks have high quantities of trace elements. Not all of them, but many of them have very high quantities. Trace elements are things like the rare earths are very important because they go into a lot of different applications. Rare earths, things like lanthanum and yttrium and niobium, and so it could be a potentially useful source of these rare earths. Now look at uranium. Uranium in some of the deposits is not too high. In India also, Indian deposits did not have very high quantities of uranium. But where we need to look at is, say, for example, you look at Morocco, and we found that 70 to 80% of the total reserves are in Morocco. Their rock has something like 185 ppm expressed as U3O8. So very, very high concentrations of uranium. There was a time when the United States was producing about 20% of its uranium for power plants and weapons from actually phosphate rock, not from uranium containing ores. Those are of course very high in uranium, but they were actually recovering quite a bit from there, and that's work which had started in the late 40s, and it had been going on. Arsenic, again, a very, very toxic stuff, and not too low, quite high the concentration. Cadmium, chromium, heavy metals. You just Look at all this. Chromium, 200 ppm. So the question and the issue that you should also look at is that I find a lot of naivety on the part of our people. I don't know if it's deliberate ploy or whatever it is, but where everybody will tell you only how much P2O5 is present in their fertilizer. Nobody seems to be asking whether any of these things are also ending up in the fertilizer, and if so, if they're ending up and if it is going into the field, can you imagine the devastation it can cause? So I'll show you some situations and some results which are of grave concern, very, very serious concern. Okay, now let us look at what is the latest situation in India. And I must have taken about a couple of hours trying to dig out information since day before yesterday for this lecture. If you look at it, and this is the 2021 figure, April to March, covering 12 months. We consume diammonium phosphate. Basically, it's the product of two ammonia and one phosphoric acid. Diammonium phosphate, 11.9 million tons. Another fertilizer called single superphosphate, 4.5 million tons. And not only that, another 11.8 million tons was consumed in the form of complex fertilizer, which is NPKs, all taken together. The P2O5 content in diammonium phosphate is about 46%. In single superphosphate, it's about 16%. It actually varies from 12 to 16%. And in these, it's about 26%. They are really formulated from DAP. So it's one and the same thing. Now, if you work out based on these percentages and the quantities, the total amount of P2O5 that we consume during 2020 to 21, it comes out to about 9.3 million tons. Our production of rock phosphate is about 1.53 million tons based on indigenous production. It is verified even from the Indian Minerals Yearbook, this mines that we have in Rajasthan, some in Madhya Pradesh. And the P2O5 was about 30%, which means we are talking about maybe about 500,000 tons of P2O5 from the indigenous or rock, which means that something like 8.5 million tons of P2O5 must have come from elsewhere. So it's all imported. Imported as what? Okay, so we can have a look at it. That the three things that India imports. One is that it imports the rock phosphate or the phosphate rock. Okay? That's and then there are factories here who produce fertilizers from rock. Okay? So that's one. A lot of people have stopped doing this, and because it was at one point very cheap to buy phosphoric acid, so they were buying in phosphoric acid and then reacting it with ammonia and making ammonium phosphate fertilizers. But now the situation has got even worse. We've started actually importing the finished fertilizers, the phosphate fertilizers, like DAP import was 6.1 million tons of DAP. And so over here it says 11.91 million tons, okay, of DAP was consumed. So we are importing this, and the rest presumably we are making from the phosphoric acid or the rock phosphate which we are acquiring. But all of this is finally coming from rock phosphate, and it's coming from imported rock phosphate. So we are extremely vulnerable. Okay? Like you have seen everywhere. Nitrogen is free. You might say, hey, ammonia and nitrogen is coming from the atmosphere. But it's not true because really the feedstock is your oil and natural gas, plus air and water is being converted into ammonia and urea. So again, we are importing something like 85% of our oil requirements, okay, crude oil. And over here you can see we are importing about 80 to 90% of our requirement of phosphorus. Okay? So, and later on you'll find same is the story with potassium. So we are in a very vulnerable situation. And I want you to realize this, that it will require huge amount of thinking and analysis and strategizing, that how exactly are we going to manage the show in India. You don't read much about it because it's all dominated by a feel-good factor of mobile and apps and this and that, and it all seems so rosy and great. But if you look at the fundamental chemicals that we require, the situation is very, very grim. So don't get overly swayed by all these things, which make it feel as if everything is very rosy in terms of IT and this, that. Actually, at the bottom, things are very bad. Okay, now let us see how exactly fertilizers are made. So it all starts from phosphate rock. So it doesn't matter whether you're importing phosphoric acid or you're importing finished fertilizers or phosphate rock. It all finally is coming from phosphate rock. So that you have to remember. If one reacts phosphate rock with sulfuric acid, and as I told you, phosphate rock is mainly calcium phosphate. So you can react it with sulfuric acid, and that depending on the stoichiometry of sulfuric acid, how much you take, you can end up with either this product, which is known as single superphosphate. It has about 16% of P2O5. Typically, that's the amount that you get, and it has got some calcium and sulfate. Okay, sulfur is also, of course, considered as a important nutrient, and that sulfur is coming from sulfuric acid. So remember, when we were learning about sulfuric acid, we also said about 80% of sulfuric acid goes into the manufacture of fertilizer. So it's really the phosphate rock and the sulfuric acid which is doing the trick. If you were to put a different stoichiometry of sulfuric acid, just so that your all the phosphate PO4 3 minus is getting protonated to form H3PO4, then you'll end up with phosphoric acid. This stuff is, as I told you, what you'll get with single superphosphate, and phosphoric acid is H3PO4. The reason why you need to do this in the first place is that calcium phosphate as such is a very inert molecule, and it is really not available to plants in substantial amount. I mean, it will leach out some amount of phosphates over time, but that cannot sustain your crops. So you need to solubilize the rock phosphate, and that's effectively what you are doing through this kind of acid treatment, which is helping to mobilize the phosphate. Okay. One also can react phosphate rock with phosphoric acid. Okay. You then end up with this particular fertilizer, which is known as triple superphosphate. Okay, this is the formula. So this is not reacted with sulfuric acid; it's only reacted with phosphoric acid. Naturally, because you are reacting with phosphoric acid, the P2O5 content here tends to be higher, 44 to 52%. This is not a very popular fertilizer in our country. But if you were to write down the equation, you can write down this. Okay, and this is effectively this molecule. Okay? This is what you're forming. Okay? Since we found that these rock phosphates have 3 to 4% of fluoride, obviously the fluoride will get also protonated, and the first molecule that you'll form is HF. Okay? But the HF, actually all of it does not get released during the manufacture of phosphor-based fertilizers. Some of it remains. Okay, and I'll discuss a little more about the single superphosphate. Is one of the most popularly used fertilizers in our country from a long time. I'll just read it out. Ground phosphate rock is reacted with sulfuric acid to form a semi-solid which cools for several hours in a den. The plastic-like material is then conveyed to a storage pile for several weeks of additional curing. The hardened material is then milled and screened to the appropriate particle size or granulated. And that is what your single superphosphate is. Whether you are making phosphoric acid or whether you are making single superphosphate, it's really coming from the reaction of rock phosphate with sulfuric acid. So if you were to have this stoichiometry, obviously 3 moles of sulfuric acid per mole of calcium phosphate, then of course you'll end up with phosphoric acid, and gypsum, because it's sparingly soluble, will be precipitated out, and you can separate it out, and this gypsum is known as phosphogypsum. So the gypsum that you get from fertilizer is not referred to as gypsum. It's referred to as phosphogypsum, but one and the same thing. It is still calcium sulfate and probably with 2H2O. When you are making single superphosphate, from whatever process I showed you, what happens is that if I'm reacting with 2 moles of sulfuric acid, it ends up forming this particular compound, and the counter ion is calcium. And of course, it will also form calcium sulfate in this reaction, but that calcium sulfate is not being separated out. And that's the reason why your phosphorus content, the P2O5 content in single superphosphate is less. So 2 moles of sulfuric acid will give you this, and 3 moles will give you phosphoric acid. Now, what happens is that when you go to do this reaction, even though it looks so simple, but you see, because calcium sulfate is sparingly soluble, and initially it is being formed as a very fine precipitate, so it can go and coat the rock phosphate. So what will happen is that it forms like a outer coating of calcium sulfate on the rock phosphate, and because of that, it can prevent the further reaction with sulfuric acid. This then becomes a problem. Even if I put sulfuric acid, the reaction is not going because of the coating of calcium sulfate. So for that, what people have done is a very creative thing, where they react the calcium phosphate with phosphoric acid, and they make this free of any calcium sulfate. So there's no calcium sulfate being formed in this reaction. And this thing does not form any coating over the rock phosphate. So after it has formed this, then they add the sulfuric acid and effectively make the phosphoric acid. So it's a very clever way of circumventing the problem of the coating of the rock phosphate with calcium sulfate, that you first react with phosphoric acid, make this, and this does not form a coating as they found, and then further this is reacted with sulfuric acid, and you end up getting this. That's not the whole story. That's only part of the story. So when you are making phosphoric acid, as we said over here, that calcium sulfate is your byproduct, right? This is what will precipitate out. This is the liquid. Okay, so you filter, you will get calcium sulfate. Now, the calcium sulfate actually has very interesting properties. The calcium sulfate that we know normally is what we refer to as gypsum, which is calcium sulfate 2H2. Then again, you have calcium sulfate, which is used like when you have a fracture and then the doctor applies a plaster, put some water in it, and it hardens to a rock, and that's your plaster. So that is what is plaster of Paris, which is calcium sulfate with half a molecule of water. You can also make absolutely anhydrous calcium sulfate, which is just CaSO4. Okay. By the way, just for your curiosity, got nothing to do with making of fertilizers. Van Toff, he describes in his Nobel lecture some very interesting work that he did trying to, when he was studying osmotic pressure, and he used certain molecules with a very high osmotic pressure to pull out the water of crystallization from hydrated salt. It's quite an interesting thing, and these were some of the early work that he describes. So the issue is that you know these have got different domains of stability. For example, if I want to make gypsum, CaSO4 2H2O, so I cook up my rock phosphate with sulfuric acid, and this is the axis, this is P2O5% and this is temperature, okay? Because P2O5% means I'm making H3PO4, I can express it as P2O5. Suppose like let's say I have a temperature, let's say around 70 degrees centigrade or 60 or 70, somewhere here. So then you can see that you will be at about 35 to 40% of your P2O5. And if you are a bit lower, say 60 or yeah, around there, you'll be around, anyway, around 35% or thereabouts. Okay? So what you would do is that if your plant is focused on producing phosphoric acid where you want calcium sulfate 2H2O to be obtained, then you'll use a reaction temperature of around 60, maybe 50 to 60 degrees centigrade, and the amount of your gypsum which you'll get and the concentration of your phosphoric acid that you'll get will be around P2O5 content will be around 26 to 32%. They are probably talking about a temperature of around maybe 85 degrees centigrade. Because if they don't do that, the rate of the reaction is too low. Okay, so this is the compromise, maybe around 80, 85 degrees centigrade. They will be cooking it up, okay, and they'll end up with with P2O5 phosphoric acid with 26 to 32% P2O5, and you'll get a stable calcium sulfate. Can anyone tell me what are the advantages of operating in this particular zone? I've told you what is the disadvantage. What is the advantage?
So less power, less energy is required.
That's one. But then, if you require more time, you have to integrate that energy requirement over time. So you may find that it's actually not helping you that much. Anything else that comes to your mind? Advantages? Let me put down. It's a good point that you made. Advantages of dihydrate process. Anything else that comes to your mind? And look at these, okay, and in comparison to these, you say, well, what happens is that, you see, this is the stable form of gypsum, whereas these are unstable forms of gypsum. And imagine if the same thing which happens when you have a fracture, you go to the doctor and he's applying a bandage like thing and then applying water and it becomes rock hard. And imagine if that were to happen while your process is going on. What a havoc it would be. I mean, all your filtration, everything, all your filter presses would be absolutely choked. You'll be in a soup. So it is very, very attractive from some points of view, but also very unattractive from some points of view. Okay? But let me tell you that this is the process that is predominantly used and operated, which is the hemihydrate process. Okay? Now, let us look at the hemihydrate. So, if you are at a temperature of, let's say, around,
Yes, sir.
yeah,
So please could you repeat the advantage?
the advantage is that, you see, if I am operating at a temperature of, let's say, around 80 degrees centigrade, which means that I will be within the phase diagram for calcium sulfate 2H2O. I'll be in this portion,
Yes, sir.
which means it's a good thing because I'm forming a probably a nice crystalline granular calcium sulfate 2H2O, which will be easy to filter out. You know? But the disadvantage, of course, one disadvantage is that the P2O5 concentration will be low, which means that I will have to have a higher evaporation cost. So that's the disadvantage. But in terms of the advantage, the advantage would be the gypsum form would be of thermodynamically more stable form, and it would probably be cooling and easier to filter. Is that clear?
Yes, sir. Thank you, sir.
But now here, when I'm operating, okay, I let's assume that I've solved the problem of what I'll do with the hemihydrate. So I go somewhere here, so about a temperature of 120, and now you can see that I will be somewhere around maybe around 40 to 50% concentration of P2O5. So between 100 to 120, if I operate, I will be making a phosphoric acid with a higher concentration of P2O5, which is good because one is that I will require less evaporation to make concentrated phosphoric acid. The second advantage is obviously since I'm operating at a higher temperature, the rate of the reaction will be higher. So from the same plant, my throughput will be more. I'll be able to get more phosphoric acid out. So that would be the advantage in this particular case. Where it is also very critical, this temperature, is that I told you that when I'm reacting with acid, and not only am I getting phosphoric acid, but the fluoride, which will be, you can think of it as if it's present as calcium fluoride, reacting with sulfuric acid will form HF. HF is not actually that volatile, and HF forms very strong hydrogen bonds with your aqueous phase, and so it's quite hard to take out the HF. Now, typically what happens is that the HF reacts with silica and it forms the hexafluorosilicic acid. So it will form this. But for that, I have to make sure that my rock has got sufficient amount of silica. If the silica amount is insufficient, then it's not going to happen. This reaction may not happen, and your HF, especially if my temperature is low, suppose I'm making only the dihydrate crystals, and my temperature is low, I'm operating at say 60 degrees centigrade, my HF may not volatilize under those conditions. Whereas the chances that it will be stripped off, volatilize, are higher when I'm operating at a higher temperature. So the phosphoric acid that I'll get will have less amount of fluoride at the higher temperature of operation, and at the lower temperature of operation, it may have higher content of fluoride. That's one. The higher temperature is also very important because these phosphate rocks come as rocks, and then they have to be ground. Now, if, for example, I want to operate at a lower temperature, then I must necessarily grind it more fine just so that I have a higher surface area. So I compensate partly the lower temperature of the reaction with a higher surface area of my substrate. Whereas if I'm operating at the higher temperature, then the reaction rates are sufficiently high that I may not need to grind so fine. And this grinding of the rock consumes huge amount of energy. So what will it do? As I'm trying to increase my mesh size, my grinding cost is going up. My reactor cost is going down because I can have a higher throughput because my surface area is higher. So my rate of reaction will be higher. But you have to strike a balance between these two. And that is what chemical engineers do so beautifully, that they are able to find these minima, which is where I would probably like to operate. And you will not only have a one-dimensional perspective and say that, if I have a 200 mesh and my rate of the reaction is much faster, or my completeness of reaction is much faster in time, I'll also have to look at the grinding cost. So that's how you strike the balance. And you have seen this kind of balance even when we were talking about the soda ash manufacture, that how tall does the tower need to be, the solvent carbonation tower. Now, let's quickly look at the advantages and the disadvantages of the hemihydrate process. As I told you, this is the more popular process because there are huge advantages. If you can manage the problem of this thing not hardening up on you during your process, the gypsum. So one is that it tends to form a purer acid, the hemihydrate process compared to the dihydrate process. There are less sulfate and suspended solids. The fluoride content will be less because of the reasons we mentioned. The grinding cost of will be lower because I don't need to grind it so fine. I'm compensating it with a higher temperature. So these would be two of the very important advantages. The disadvantage could be that the hemihydrate crystals, as I was mentioning, are not as well formed as the dihydrate crystals. So the filtration tends to be more sluggish, takes higher pressures to filter. And secondly, if I cannot filter well, the amount of the moisture in my wet cake will be higher. If I've got a perfectly granular thing, all the liquid will flow out and I will not have much moisture content in my crystals. But whereas if it is not really filtering so easily, you'll find that the moisture content, here when I say moisture content, it means the phosphoric acid content, will be much higher in my wet cake. And so I then have a problem of again getting rid of that. So your purification and washing steps will become much more elaborate if I have got a hemihydrate process. The other is that in case, as I told you, that if for any reason there is some topsy-turvy thing happening in your process, and if it reverts to calcium sulfate 2H2O, then you have had it. If you have not done it in a controlled way, then you'll be in a big problem. So those are some of the disadvantages of the hemihydrate process, and the advantages are also very clear.
So can you please explain the advantages again?
See, the advantage is that when you are reacting this at a higher temperature, one thing is that if you have got volatile impurities which are forming, like the HF or H2SiF6, those things will get removed from the phosphoric acid relatively more easily than at lower temperature. And what they have also found is that the sulfate content, the free sulfate, will be less because what happens is sometimes all your sulfuric acid is not necessarily reacting with your rock phosphate and forming gypsum. You may have taken a stoichiometric amount, but some amount may remain unreacted, and that will show up as free sulfate in your phosphoric acid. In terms of impurities, these are the two very important things. The third, it's not mentioned here, but capital savings will come because I have made a phosphoric acid with a higher concentration of phosphoric acid. And therefore, my capital investment in terms of evaporation will be lower. Okay. So let me also put that down.
So, but won't higher amount of energy will be required?
One second. Investment in higher evaporation load. Yeah, see, this is the interesting thing, and that's what, again, let me tell you, it's a very good question, which you had even asked earlier. Uh, won't evaporation, no, won't energy cost be higher because of higher temperature? That's what you're asking, right?
Yes, yes.
Okay. See, now what you have to do is that you have to take a much more holistic view. At the end, I'm trying to make phosphoric acid with a certain concentration. If I make it at the lower temperatures, that's fine. One is that my rate of reaction is lower. So temperature per se alone cannot dictate it. I will have to see over how much time I'm applying the heat. Okay. So I have to integrate that and I have to see the total amount of energy that I consume. Second, because my phosphoric acid is being formed with a lower concentration of P2O5, so I will have a much higher evaporation load, which I'll require energy for. So I'll have to see the sum total of the energy requirements for all of these with the ultimate objective of producing phosphoric acid with a certain concentration of phosphoric acid. So I cannot only look at the reaction and make that decision. Is that clear now?
Yes, so now it's clear. Thank you,
Okay.
sir.
So let's look at this process in some detail. Right? So in the hemihydrate process, as you saw, you'll end up making about 40 to 50% P2O5 in the phosphoric acid. Now, you're taking in phosphate rock, you're adding sulfuric acid, okay? But you don't actually, I'll show you the cleverness of this process, okay? And obviously there is a heat which is applied, okay? Now, the heat is not really so much required because it generates huge amount of heat, and that itself will lead to a rise in the temperature of this reaction mass. If the temperature rises uncontrollably, then of course you can have a problem. So what you need to do is that the way the temperature of this reactor is controlled is through flash cooling. Flash cooling is a type of adiabatic evaporative cooling. So if you pull a vacuum and so under those temperatures, water will start evaporating and the latent heat that goes in cools the rest of the mass, So that's how you really cool down this thing with the flash coolers. The vacuum also serves another purpose. When you are actually doing this reaction, sometimes what you'll find is that some of the solid material could have entrapped gases because gases like HF, etc., are being formed. Now, once you have got these kinds of slurries with entrapped gases, it can alter the viscosity profile of that slurry. And that can make pumping quite difficult. So the vacuum actually serves that other purpose, that you also are degassing the reaction mass besides doing the flash cooling. You have a scrubber here, and that scrubber is actually taking waste gases which are being formed. And then in the hemihydrate process, I ended up forming CaSO4 half H2O. Now you have got a hemihydrate filter. Now what these people must have done, and the Japanese are the ones who I feel have got the best technology, companies like, I think, Nissan. They, I think, have done something extremely clever by way of putting in some crystal habit modifiers which help to retain a favorable morphology of the crystals, even though they are hemihydrate, half H2O, and they're able to keep it stable, so that it doesn't dihydrate upon you. So then you're filtering, and you're getting your phosphoric acid over here. Most of the phosphoric acid you'll take out here, but then you'll also wash the filter cake, okay, so that you're removing as much of the phosphoric acid as possible. But then it will be dilute phosphoric acid because you've added water to this cake. And again, what you do over here is that you then take the hemihydrate and you do a very controlled hydration with water and forcibly convert it to CaSO4 2H2O. So you are ultimately making the dihydrate, but you're doing it after the reaction, not during the reaction. During the reaction, you made the hemihydrate. And the ingenuity of material science, of solid state physics, etc., all will come in here. How to do that smart stuff of inhibiting the CaSO4 half H2O from solidifying on you, and at the same time, in a controlled way, then hydrating it so that you ultimately end up with the dihydrate. Now, the weak phosphoric acid that you get over here, you just put it back here, because what did we say? That otherwise, if you form calcium sulfate and it coats, then it's a problem. So what you do is, the sequence is important. They must be taking the weak phosphoric acid, reacting it with the phosphate rock, just so that the gypsum is not formed at that stage and the entire mass is getting solubilized. At that point, you add the sulfuric acid so that you don't have that problem of caking of your solids. So that's the sum and substance of the whole process, by which phosphoric acid is made by the hemihydrate process. Subsequently, downstream, you may have to do some purification. You can do it by solvent extraction. Maybe I'll discuss that tomorrow.
So
Is that
I have
clear?
a small doubt, sir.
Yeah.
So in the digester,
Yeah.
so I mean after the digester, what exactly happens
What
with the
happens is,
hemihydrate?
in the digester, now at this point you're producing hemihydrate, because I'm doing it at the temperature of around 110 degrees centigrade, the reaction. So I make CaSO4 half H2O because I'm in that domain of the phase diagram where the half H2O will form. Okay.
Yes, sir.
So I'm now filtering it. Okay? It's a solid. Okay, I'm filtering it. And obviously there is some clever manipulation which was done by these people who have mastered the art of the hemihydrate process, where they prevent the undesired kind of rehydration of your hemihydrate unless you command it and you want to do it. So that's what they're doing. They're keeping it stable, and later on they're introducing hydration tanks where they're putting a very controlled amount of water and converting the CaSO4 half H2O into CaSO4 2H2O, and that's
So
what they're
but
finally filtering.
they from the dihydrate filter, they are using the phosphoric acid to prevent the coating, right? So why not?
No, not from the dihydrate, from all the filters. Everywhere you'll get traces of phosphoric acid now when you filter the
Yes,
solid.
sir.
So all of them are being piled up and being put over here.
Okay.
Okay. Huh?
Yes. Thank you, sir.
All right.
Thank you, sir.